Hello everyone and welcome back to another episode of Power Logic. So today, aside of what we traditionally do, which is just AMC10 and AMC12 solutions, we're going to be doing an interesting problem. So first I'm going to introduce a type of data structure in computer science, which is a binary tree. For example, this one is just a really simple binary tree, and binary tree is defined as for each of these nodes, there will actually be two extensions that are called the children of this parent node. So, for example, this will be a two-layer binary tree, but if we keep on extending, then this just becomes a 3 layers, and there will actually be a total of 1 plus 2 plus 4, which is 7 nodes. So some interesting fact. There will actually be 2n minus 1 nodes for the n layer binary tree. So what is the problem that we're trying to solve? We are trying to determine the value of this double summation So what do I mean by that? So, for example, for this two-layer binary tree, we can number each of these nodes as giving them a number 1, 2, 3, 4, 5, 6, and 7. So, from here, we can essentially realize what do we want to do with this summation. So this summation is basically saying that we want to find the distance from any of the node, for example, just this node to this node, like any two nodes, and sum them up to get our final answer. So for example, the distance from 2 to 7, that is just simply 2, we have to actually go through this, this, and this. So basically distance of 2 and 7 will just be simply 3. However, we need to also account for the distance of 7, 2, because since we're having this double summation, then basically there's actually overcount. From A to B and from B to A are both included in this summation. So therefore the total, let's call it interaction of these two, will just be 3 plus 3 just equal to 6. So let's just do a two-layer binary tree for fun to find how many are there. So let us first count from this node. This node we have to go once to reach this node, but we need twice 2 roots to get to this node. So basically for this tiny little one here is just 1 plus 2. But for this one, we don't even have to count again because this binary tree is actually symmetrical. So this means that the total number of roots that this node can go to reach any others will just be the same with this. So essentially, without even calculating, we can just know that to reach this one will just be 3. What about the blue node? The blue node, we go with this root one step to reach this red one, and same analogously one step to reach this one. So basically, the total will just be 8. Okay, so we can easily find the number of such roots that value the summation with a 2-layer binary tree. But what if our binary tree is something like this? What if we have something like 20 layers? Then how are we going to even possibly solve it? Well, we know that 20 layers must be like a really giant number. So let's try to see what about a 3-layer binary tree? 3 layers we have a total of 7 odd in the 3-layer binary tree. So you might think that, well, this won't just get too bad, right? We can even just manually count. Well, yeah, sure, we'll just manually count and see what is going to be the value and how big it will be. So first, we can start from the bottom to the top, or actually possibly from top to the bottom would be a better idea. So from here, let's first divide into layers. So first, for the first layer, we can reach the second layer, right? Ending out from the second layer and also ending out from the third layer. So basically, in order to reach, well, let me just mark this to be number. Well, in order for our first layer to reach the third layer, we must take 2 steps, like for any knot, right? So from here, we can go 2 steps here, 2 steps, 2 steps, and 2 steps. So from 1 to 3, we're going to just have 8. And what about from 1 to 2? Well, 1 to 2, we have one for this and 1 for this, so just 2. Now, what about from 2? 2, we can just consider going from 2 to 3. Well, why is that? Why do we not consider from 2 to 1? Because 2 to 1, each root must be the same number with 1 to 2, right? Because you go from here to here, it's the same as going from here to here. The distance would actually not change. So basically, this tells us that we can just find from the top to the bottom and multiply the entire thing by 2. That will just give us our desired result. So from 2 to 3, that will just be 1 step for each of them. So 1 step for each of them, and times 4. So 2 to 3 will just be 1 times 4. But is that it? Well, it's not, because from 2 to 3, we also need to consider when this one goes to this position. So what would that be? 2, we actually just have 1 to go here and 1 to go here. But now we also have to consider when they go to this direction. So it'll just be plus 3 times 2. Now 1 plus 1 plus 3 times 2, and then we also have to multiply by 2 because it's also the same way if we want to go from this knot to any of these two. There will also be 3 steps. This seems to be pretty interesting, isn't it? Now, what about, we can also have from 2 to 2. So what does that mean? Two to two means that we just go from here to here, and there's actually 2 times each 2 steps, so there will just be 4 steps. And just evaluate this really quick. This is just equal to 16. But now, what if you want to go from 3 to 3? This seems to be not that fun. So let's just consider this knot. So if this knot want to reach this knot, then we only need 2 steps. But if this knot want to reach this knot or this knot, then it's actually the same number of steps. So how many would this take? 1, 2, 3, 4, and 1, 2, 3, 4. So there will actually just be actually should be 2 plus 4 plus 4. So from any of the 3 to the other 3's, this will just be equal to 2 plus 4, 4. But remember, it's actually symmetrical. So you'll multiply by 4, which gives us 40. By the way, this already accounts for both of 1, 2, 3 and 3, 2, 1. And this one also accounts from 1 to 2, and also back to 2 to 1. And this accounts for 2 to 3. But we actually didn't account for 3 to 2. Well, this one will just be the same. 2 times. So this will just be it, which will just gives us 20 plus 32 plus 4 plus 40, which is equal to 96. That is a really big jump from the binary tree with only 2 layers, right? 2 layers will only have 8, but 3 layers already have 96. So now, what is the general way to solve this problem? Now if we did not realize, then I'm just going to possibly spar a little bit. Instead of looking at node, we're going to look at each path. For example, this path here. Which two nodes, if we take, are going to pass through this path? Well, in order to reach this path, we must choose one from this pile and one node from this pile, right? In order for this to be connected. Like, if we just assume that that this part is a strongly connected component and this part is a strongly connected component. So we must need this part to connect these, to walk from this to this. Because there's no way for you to walk from here to here since this is not strongly connected from the other way. Or if we walk to here, and that still does not help since these two are not connected, obviously. So what about if I want to walk from here to here? Well, obviously you're not going to pass past this point, since you can just go from here to here directly. So the minimum distance, you do not want to just go into this route, since this is unnecessary. So can I say that prove this claim that we must pass this route if one node is chosen from this pile and the other node is chosen from this pile? Well, yes, because this is actually the only part that is connected between, right? This is actually one of the properties of binary tree. So if I add another route from here to here, then this is not really necessary, because if I choose one from here and another one from here, then the shortest path will not be between this, but it will be going here, here, and here. This will be fastest. So we'll not have to pass through this. But we're actually in a binary tree, so this assertion actually would not work. So basically, choosing one from this pile, we actually have 3. So for this path, we're actually going to have 3 choose 1 from the left pile and 5 choose 1 from the right. No, 4 choose 1s. Excuse me. 4 choose 1 from the right pile. Now, can we do the same with this route, because it's symmetrical? So it'll just be 3 choose 1 times 4 choose 1. Now, what about this route? Well, this route, we must pass through this path in order to reach this node. Same as this, same as this, and same as this. Well, we must pass this path regardless of which node we decide to start. So this basically means that, so if I use a combination, then this will just be 1 choose 1 times 6 choose 1. And same as this. So we just add up them to see what we get. Now this one gives us 48. But you might be asking, well, where did the factor of 2 go? Well, if you think about that, we only account, so basically choose one from this pile, right? And choose one from this pile, assume that it's just this route right here. Then we did not, we only consider when we go from A to B, but we did not consider when it's from B to A. However, from this problem statement, ij and ji can be swapped and they still have to be added. So therefore, we have to actually multiply this entire thing by 2. This will give us 96. Well, let's go back to the 2 layers. Well, for a 2 layer, for this path, we actually have how many ways? For this path, we have to choose one from this pile and one from this pile, which this essentially just gives us 2 times 1. And so, because it's symmetrical, this will also be 2 times 1. By our idea, this will just be 2 times 1 times 2, and multiplied by 2, which gives us 8. Now, thank you for watching for this episode, and in the next episode, we're going to try to actually derive a formula for n layers. So it will not just be 1, 2, 3, 4, 5, 6, 7, 9, 10, that are simple numbers, but possibly if we also have like 20, and we can still try to use this idea of trying to pile them and also choose one from each to find like this entire summation regardless of the value of n. And see you next time.